All right, any queries? All right, so we'll see the application of what we. Yeah, excuse me, do you have any queries?
Sir, I can't hear you.
You can't hear. Okay.
No, sir is audible.
Okay.
You are audible, sir.
Okay. So we'll apply what we have studied yesterday to the Pelton turbine or Pelton wheel. Okay. Now, to refresh your memory, here is a schematic of a Pelton wheel. So this black circle represents the disc or wheel on which buckets are mounted. And this small circle here is the shaft, and this plus sign is the center of the shaft. Okay. So you have a nozzle which I have shown in red. A jet of water will be directed from the nozzle to one of the buckets. So in this figure, I've shown only 4 buckets, but there will be large number of buckets in general. So the water jet will strike the bucket and it will be deflected. So let us see how to predict the power generated by this Pelton turbine. And it will obviously depend on certain parameters. So one of the things that you can guess is it will depend on what is the speed of the water jet at the exit of the nozzle. Okay. So this is the view, enlarged view of the what you may call the bucket. So it has a symmetric shape. The water jet, after striking the what you may call the splitter plate or ridge, the jet will split into two and it will be deflected backwards towards the oncoming jet. Okay. So we can do this analysis taking a control volume which I have shown here in green. Okay. So this section I've called 1. So as you can see, the fluid will enter the control volume through this section. And section 2 and section 3 are outlets. So this blue line here is the interface between the water jet and air. You have air above and air below. Okay. And if the radius of the wheel is large, okay, the rotary motion of the buckets is almost equivalent to a translatoring motion with a speed, velocity in this direction, and speed which is the radius of the wheel multiplied by the angular speed. Now we'll apply momentum balance to this to estimate the forces on this, what you may call vane or blade or bucket. Okay. So I want to emphasize that the buckets are usually symmetric about the ridge, and the blade angles of the two streams are equal. So here is another small view. Okay. So you see the oncoming jet is deflected through an angle which I am calling theta. Okay. So the angle through which the jet at the bottom is deflected and the jet at the top is deflected are usually the same when the shape is symmetric. Okay. Now we define another angle which is called the blade angle, which is the angle between this tangent to the surface and this horizontal here. Okay. So if I call this blade angle beta, this is the section 2 I'm calling beta with a subscript 2, and this is section 3 I'm calling it beta with a subscript 3. And W vector 2 is a relative velocity vector at this outlet. So this, from the kinematic boundary condition, we can guess it will be parallel to the surface. And W3 will be also parallel to the surface of the bucket at this point. So the flow is open to the atmosphere, and the turning of the jet results in a change in the momentum of the fluid. And the force exerted by the impinging liquid will push the bucket away, and another bucket will come, and it will be similarly acted on. So
Sir,
yeah.
so that beta 2 plus theta 2 equal to 180. Like, do they add up to 180 degree?
You mean this theta should be 180?
No, theta plus beta.
Theta plus beta will be 180, right? Okay. So I've written here the angle of deflection is equal to pi beta. Pi is in radians, and beta is the blade angle at the exit. Okay. So later on I'll show you the velocity triangle, and you'll see it is the angle between minus of u and w. Okay. And this convention will be used when we looked at the centrifugal pump as well as the Francis turbine. Okay. So you're definitely right. Theta plus beta is 180 degree. So the jets of liquid will lose their kinetic energy, and that reduction in the kinetic energy of the liquid will be the gain in kinetic energy of the blade or vane or bucket, whatever you call it. Okay. Now I've gone through all this. If you want, I can just show you one figure. Okay. So here, this is the Pelton wheel at the bottom over here. Okay. So you have an upstream reservoir. This could be at the top of a hill or mountain. This is called headwater. Okay. And this is called tailwater. So there are two reservoirs. The water will flow from the upstream reservoir at the top to the downstream reservoir at the bottom. Okay. So you have air above, and there's a shallow pipe called pressure tunnel or pressure pipe through which the liquid will flow. It's usually water. Okay. It will fall through a certain distance, go through the nozzle, and it will be directed into the bucket. So one of the parameters which will come into play as we see later is this height difference between the level of water in the upstream reservoir and the center line of the nozzle. We'll call it the gross height or gross head, H with a subscript GR. Okay. Now, as I've said before, we want to predict the power developed, and in this class we'll use a simple model which assumes the flow to be invisible.
Sir,
Yeah.
what is the use of that surge tank in the last figure?
Pardon?
What is the use of this surge tank? Surge tank.
Oh, surge tank. Okay. The surge tank will damp out pressure transients and velocity transients. Okay. So when you start it from rest or there are fluctuations in the power load that is required by the turbine. Okay. There may be oscillations in the flow rate. Okay. And that may lead, may call a water hammer. Okay. So large pressure pulses may develop. Okay. So if you have a tank over here, the water in this tank will go up and down and kind of stabilize the situation and damp out this transients during load changes. Okay. So what is the impact of the load that we'll discuss later? Okay. First of all, let me find out the power developed, and then we'll show you that at steady state the power developed and the power required must match. Okay. So when there are changes in the power requirements, you need to make certain adjustments. Okay. Okay, and the vertical pipe is called a penstock. And you want to reduce the head loss here, so usually the diameter will be large. Okay, now let us see how to analyze it. So we'll use a global approach. Okay. Now, if you look at any undergraduate book on fluid mechanics, right in the beginning you will have a chapter where you solve problems using a control volume approach. So there you will see that you are applying the balance of momentum and conservation of mass to a large chunk of fluid. So we'll call it a global approach. Okay. Now in this case, the control volume which I just showed you was attached to the bucket which is moving. So we have to use a moving control volume. And that is why I've spent so much of time in developing those equations instead of just stating them. Okay. Now the mass fluxes and momentum fluxes crossing the control volumes need to be evaluated. And again, we'll use a simple model where we'll assume that at those inlet and outlets, the flow is one-dimensional or quasi one-dimensional. That is, we'll assume the velocity distribution to be uniform. Now there are three equivalent approaches. One is using balance of angular momentum. Okay, so that is appropriate because the wheel is rotating, but we have not yet developed in detail this principle and how it applied. You may have solved problems where you looked at flow through a lawn sprinkler in your second year. Am I right? Have you solved the lawn sprinkler problem? Well, you might have forgotten, so I'll leave this for later. Okay. You can use balance of total energy of the first law of thermodynamics, and we have discussed this to some extent. Okay. Now, most books will give you a prediction using the third approach, which is the balance of linear momentum. So that is what we'll do today. Now, as I said before, if h is the height of the bucket and rp is the pitch circle radius or mean radius of the buckets, then if h by rp is much less than 1, you can assume that the fluid interacts with the rotor at a fixed radial distance, which is the pitch radius of the wheel or the mean radius of the flow. Okay, that means if I use the principle of balance of angular momentum, the moment arm we can approximate at both the inlet and outlet by the radius of the wheel. Okay, and that is why the balance of momentum and balance of momentum will give you the same answer. Okay, that will give you the same answer only when you say the moment arm is constant at inlet and outlet. So we'll use a simple analysis. Momentum. First, let us use linear momentum analysis rather than angular momentum to a translating control volume fixed with respect to what you may call in engineering terms as a developed or unrolled section of a bucket or blade. And the speed u of this translating control volume is the mean speed of the buckets, which is the pitch circle radius times the angular speed. Now in this equation, you want u to be in meters per second. So you express rp in meters when you solve problems. We may give you the data in centimeters, convert it to meters. And then this omega must be radians per second. Okay. Now quite often engineers will talk about the RPM or revolutions per minute. Okay. So if n is the RPM, then n by 60 is the RPS or revolutions per second. And the angular speed, you know, will be 2 pi times that. Okay. So you have to convert RPM or RPS to radians per second and then get the mean speed. So here I've shown the control volume And O prime, X prime, Y prime is a frame which is attached to this moving bucket, which is translating. So this is a translating frame. And it's translating such that the axis O prime X prime is parallel to the axis OX, and the axis O prime Y prime is parallel to the axis OY. And this control volume shown by the green dotted line is moving or translating. Now we'll apply the balance of momentum to a system which is coincident with this control volume at time t. Okay. So as you can see here, I've taken a simple approach where inside the control volume you have a solid as well as liquid. Okay. But this solid also is a rigid body and it is also a continuum. Now let us look at the forces which are acting on the system inside this control volume at time t. Now I have not shown the body forces. I've just shown the distributed force due to pressure. So you see that on the right over here, right of the vein or bucket, the pressure will be atmospheric pressure because it's exposed to the atmosphere. Now here I have not written PATM because writing PATM all the time will make it cumbersome. So I have simply written PA is the same as PATM. Okay, so you have air on this side, air on this side, and air on this side. So if you look at, say, this surface, okay, that is, we'll call it the free surface of the jet. Okay, you have air. So obviously here also the distributed force will be constant, and the intensity will be your atmospheric pressure. Now, if you look at section 2, okay, here you have liquid here, it's not air. Okay, and similarly at section 3 here, this control volume is cutting through the liquid. Okay, but as we have discussed, if you look at this as a circular jet or circular cross section, or on the periphery of the jet, which is exposed to the atmosphere, the pressure is atmospheric pressure. And if you look at the streamlines which are crossing this section 3 or the section 2, the curvature is negligible. So centrifugal effect is small here, unlike here where there is a large curvature. Okay. So the pressure inside may be assumed to be atmospheric pressure. So if you consider fluid particle here at the exit, just outside the exit, there is no net force due to pressure because the pressure distribution is uniform. So the acceleration of the particle will just be equal to the gravitational acceleration, approximately. So now, of course, there will be a resisting force if the wheel is spinning at a constant angular speed. It means there must be a load on the shaft which will come from the generator. It may be due to electrical load. So that resisting load in this model, where we are assuming the rotary motion is equivalent to a translatory motion, is shown in this model by an external force which I am calling F with a subscript B. B for blade. Okay. Now there must be an external force on this to keep it from accelerating. Okay. So there is a change in momentum because of which there will be a net force. So I have not shown the force due to gravity, which will be in the vertical direction, OY direction. We are interested mainly in the forces in the X direction. So I have not shown that here. So in the X direction, in the negative X direction, there must be a resisting force here. Otherwise, this bucket will start to accelerate. So we want to predict the power when the turbine is operating at steady state. That is, the angular speed is constant. Okay. Now I have shown you that if you have a distributed force due to pressure at all points on the control surface which is uniform, then the net force is 0. Okay. I had asked you and you had guessed that it will be 0, the net force, due to cancellation effects. But I've also shown you rigorously using the Gauss divergence theorem why it should be the case. Okay. Now, section 1 is the inlet, section 2 and 3 are outlets. So there are two outlets. So what we are assuming is that the bucket height is small compared to the radius of the disc, and that the fluid will behave like an inviscid fluid. That is, viscous forces are negligible. Otherwise, the analysis is too complicated. Then you have to solve the Navier-Stokes equations using techniques of CFD. Now, the important thing is that, and I've discussed this in detail, the flow will be steady in the frame of reference which is translating. Okay. Now, I had shown you this before, but at that time I had not explained what this means. Okay. Now, after the discussion we had using the Galilean transformation, it has become clear to you what is the difference between the temporal derivative in the stationary frame and the moving frame. So if you go back and look at this, you have a relative streamline pattern, and if you have an observer sitting and riding with the sitting on the bucket and riding with the bucket, so in the moving frame, he will see a stationary streamline pattern, not moving. So the flow is steady relative to him. But if you have an observer sitting on the left over here at the ground, he'll see this same streamline pattern translating to the right. So if the streamline pattern is changing with time, then the flow is unsteady in the stationary frame, but it will be steady in the moving frame. And the fourth assumption I've already explained again in detail today. The pressure inside the liquid at section 1, 2, and 3 will be atmospheric pressure, and I've discussed the reasons why. Now, if you look at Fox and McDonald, they'll make a simple assumption without any justification. They'll assume that there is no change in the speed of the water jet relative to the bucket as it slips along the vane or bucket. So I've given you a rigorous justification of this in the previous class by deriving Bernoulli's equation in the translating frame. Now I have already uploaded 4 more documents yesterday. You might have seen that. Okay. So if you go through that, you will see that in one of them, I've shown you that the relative velocity magnitude at all points on the surface, inside surface of this bucket will be the same. So the prediction that we are making now, we have to choose first of all an appropriate translating control volume, and we'll discuss 2 possible choices. Today I have taken the simplest possible, one that cuts across the solid surface. So this control volume includes not only the fluid, which is water, it also includes the solid. The advantage of using this control volume is that the net force due to pressure, as you can see here, is 0, which is obvious at a glance. Now we'll consider a system, or what authors of fluids will talk about as material region, because the matter inside always has the same identity. So we'll consider a system which occupies the control volume at time t. So at a later instant of time, the control volume would have moved in one direction and the system would have moved in another direction. So, and even at a previous instant of time, they will not be coincident. But we are considering a coincident control volume, which means that the position of the material region or system and the control volume is coincident at time t. And at time t, you can apply global balance of momentum, linear momentum. So if I say L vector is the linear momentum and with the subscript SYS for system, then it's just Newton's law. The rate of change of the momentum, as seen in this stationary frame of reference, is the net force acting on the system. And to get L system, you have to integrate V dm, and dm is rho dv. So here rho in general and v in general can vary with position and time, But after you integrate and plug in the limits, which are time dependent, you get a scalar quantity which depends only on time. So that is why this is a total derivative. Now it's convenient to work in terms of the relative velocity, that is the velocity of the fluid as seen by the observer in the translating frame. So you can call it W or V prime, which is the absolute velocity minus capital U, which is the speed of translation of the control volume. And this V is the fluid velocity as seen by an observer sitting on the ground. Okay. Now since I've called that translating frame O prime, X prime, Y prime, you can call the velocity V prime. However, writing primes all the time may be cumbersome, so I'm introducing an alternative notation, which is the vector W, which is the same as V prime. And this symbol, as you may know, it means they're identically equal by definition. Now, what you can do then is write V as W plus U, and then you have L system is rho times W plus U. So this I can write as the sum of two integrals. Okay. And since U is independent of the spatial coordinates, it could in general be a function of time, but only of time, because it's just a translated emotion. Then I can pull this U out of this volume integral, which is the integral over the spatial coordinates. Okay. And you recognize that integral rho dV over the material region is nothing but the mass of the system, which I'm calling M with the subscript SYS. And this other quantity here you can call the relative momentum, L system with the superscript REL, which is the momentum as seen by an observer in the translating frame. So instead of the absolute velocity V, we just have W over here. So then it's convenient to write the absolute momentum as the relative momentum plus mass of the system into U. So the rate of change. But other thing is that if you apply global conservation of mass, then ddt of M system will be 0. So M system is a constant. So ddt of L system, the linear momentum of the system, the absolute momentum is the rate of change of the relative momentum plus system into du dt. But we are looking at a case where the turbine is operating at steady state. So angular speed is constant. So the bucket is not accelerating. This capital U is a constant velocity. So du dt is 0. So therefore, the rate of change of the absolute momentum and the relative momentum, they are the same. So this leads to Newton's law in the translating frame. Now this is not surprising, is it? Because this frame is also an inertial frame. If it's not an inertial frame, then you will have this additional term M system into du dt on the left. So in your secondary, you might have solved problems where there is an acceleration. But in this case, we are not looking at the acceleration. Okay. Now L system relative then will be this integral over rho times W, the relative velocity dV. So we have to apply this. Okay. Now it's convenient to use the form of Reynolds transport theorem in the translating frame, which I have shown. So this total derivative here, ddt of integral over Rm, I can write as sum of two terms. One is integral over the coincident control volume, and this is the temporal derivative in the moving frame. And you have the flux term. So this flux is carried by this W dot and the relative velocity, and here you have W. So this also is W. So I've written here W dot in parentheses because this is a scalar and this is a vector. Now what is the net force on the system? It is the force, external force on the blade, and the force due to pressure, which is minus N P and dA. The minus sign is there because it's a compressive force. And FB is minus FB times the unit vector in the x direction, because it acts in the negative x direction. So this is the external force which prevents the blade from accelerating. Now we have shown that P and dA is the same as P gauge NDA. Where P gauge is the gauge pressure, that is P minus the atmospheric pressure. So if you look at a book written by an American author, they will spell gauge pressure as GAGE. Now the gauge pressure is zero at points on the surface of the control volume which is exposed to the atmosphere, because there the pressure is atmospheric pressure. And the gauge pressure at points inside the liquid crossing 1, 2 and 3, it may not exactly be at gauge pressure. May not exactly be zero, but we are assuming it to be zero. Justification I've already given. The jet is surrounded by air all around and the centrifugal effect is negligible. So the gauge pressure is zero everywhere. So if you indicate 0 NDA, you are going to get 0. Okay. So the net force due to pressure cancels out. And the sum of the force is simply the vector FB, which is minus of the magnitude FB times E prime X. So if I look at the balance, so here I had looked at the vector equation, the balance of the vector. One can look at, so this is equivalent to 3 scalar equations, and we are interested in the x direction, x component of this vector equation. So I can replace W by Wx, and this W by Wx, and this will remain W dot n, and this will be sum of Fx. Okay. So if you apply Reynolds transport theorem in the translating control volume, you will have the unsteady term here and this flux over here. Now I'm looking at balance of x prime momentum. So this is Wx or Vx prime, and this is summation of Fx prime. Now, as yes explained to you in the last week, by looking at the airplane which was moving, okay, here you have a similar situation. The flow is definitely unsteady in the ground frame, but in the translating frame is likely to be steady. So del del t prime, which means del del t keeping x prime, y prime, z prime fixed, will be 0. Okay. So the first integral will be 0. And that is the reason why we are using this form of Reynolds transport theorem. I could have written also here Wx but v dot n here, and then this would have been del del t. And then this term will be non-zero. And the sum of forces in the x direction is minus Fb. So you have a simple relation that the flux of x momentum, relative x momentum, through the control volume is the negative of the external force on a blade. So now let us look at the momentum efflux from the control volume. Okay. So the control volume surface I can split into section 1, 2, 3, and so I've written this as a sum of 4 integrals. One is the integral over section 1, which is the inlet. I'm calling it del R1. This is del RCV, the boundary of RCV. And this is the one of the outlets, integral of, so function that you're integrating is the same. So this is over outlet 2, this is over outlet 3, and this is the remainder, which I'm calling del RCV minus this. Okay. Now, let me show you the figure over here. All right. This is what you may call the velocity triangle. So relative velocity vector we are calling W2. So if to that if you add the velocity of the translating control volume, which is U, then you will get the absolute velocity of the fluid, which is V2. So an observer sitting on the ground will see the fluid coming out of the bucket, not tangent to the blade, but at a different angle. But an observer sitting in this frame on the right will see the fluid moving smoothly out tangent to the blade. Okay. And you can see this angle, which I'm calling beta with the subscript 2, is the angle between the vector minus U and W2. Okay. So this is your W2 x or x, the component of W2 in the x prime direction. And this, if you look at this right angle triangle, this vertical distance, which I've shown in dotted lines using green, represents the y component of W2 as well as the y component of V2. And if you look at the x component of V2, it is W2x minus of U magnitude. Okay. So this is the, you have air above, air below, this is the water jet, okay, which is deflected. And you have a similar triangle at the top. So relative to the vane, the relative velocity vector will be tangent to the surface of the vane here. Okay, and to that you add the velocity u of the origin O prime of the moving coordinate system, then you will get the absolute velocity v3 at section 3. Okay. Now, so as you can see, if I go back and look at this figure, okay, if I look at the outward normal to 1, it is in the negative x direction. Okay. So first let us look at section 1. Your n1 is minus cx prime, and w1, the vector relative velocity, is the magnitude which I am calling scalar w with the capital letter, the subscript 1, and the direction is in the positive x direction. So w dot n is minus w1 ex dot ex, which is 1, so it is minus w1. So when w dot n is negative, it means that fluid is entering the control volume because n is the outward normal. So this is what is called influx. So influx is a negative outflux. And Wx in this case is W1. So if I want this integral, the contribution to the momentum flux only from section 1, that is integrated over del R1, then instead of Wx I can put W1, instead of W dot n I can put minus W1. And the integral I simply assume that the function that you're integrating is a constant. So integral of dA is area of this section which I'm calling A1. So this is the momentum efflux, which is negative, so it is the influx. Now look at section 2. So if I go back to this figure, okay, the normal vector is tangent to this, is parallel to this vector W2. So you see that W2 and N, it has a negative x component and a negative y component. And if you look at the x component, it will be cos of beta, and the y component will be sine of beta. Whereas here at the top, it will have a negative x component but a positive y component. So if I look at N3, the outward normal at section 3, it will be minus of cos beta 3, but it will be times Ex, that's the x component. And the y component will be plus sine beta. So on section 2, N2 is minus cos beta into this, you can call it I or I prime, whatever it is. I prefer to use E subscript x, and this is E subscript y. And W2 is the magnitude of W2 into N2. And W2 dot N2 now is simply W2. So this is positive, which means that this is an outlet. But Wx here is negative. If I go back and look at this figure, positive x prime is pointing to the right. And as you can see, W vector is slanting downwards. So its x component is negative. Okay, so you have rho times minus W2 cos beta 2 into W2 A2. Now you will have a similar thing on section 3. Only difference is that this will be plus sine of beta 3. Okay. And here it is similar, just you have W3 A3 and minus W3 cos of beta 3. Okay. Now I have a suggestion which it might be useful for you when you solve problems. That is, when you write this equation. So here what I've done is first I split it into 4 parts. Okay. And the integral over the last part is 0 because W dot n is 0 on this last part. Okay. Because those are stream surfaces, relative stream surfaces. So the normal component of the relative velocity is 0. Okay. So this integral representing the momentum efflux has 3 main contributors. One is the quantity integrated over R1, other over R2, and other over R3. Now below this, I suggest that you write down the signs. So Wx was positive on section 1. Okay. So what is section 1? Let us see again. This is section 1. So Wx here will be simply Vj minus the speed u. But it will be, usually you will not have, it's not possible to have u larger than Vj. So it will be coming in. Okay. So Wx is positive, but it's an inlet. On an inlet, W dot N is negative. So if you look at the signs, Wx sign is positive and W dot N sign is negative because this is an inlet. On the other two, the sign of W dot is plus. Okay. But because the jet is deflected backwards, your Wx is negative. Okay, as you here, this vector is pointing, slanting downwards, so Wx is negative, and this is slanting upwards, Wx is negative. Okay. So what is the bottom line? If you look at it here, plus times density obviously will always be positive. So plus times minus will give you minus, and here minus times plus and minus times plus. That means all these three terms will be negative. So this sign here is important. Sign has a physical significance. So if you make an error in the sign, then your whole answer will be wrong. Okay, so I make this suggestion every time I teach a course on fluid mechanics, that write down the signs below so that in your mind, when you see the final result, you can see whether or not you have made any careless error. Okay. So come over here and let me write down this. Okay. So from the section 1, you have rho W1 into minus W1A1 because this was the inlet. And from the other two, it was outlet. So W2 plus W2A2 here plus W3A3. But the velocity x component is negative. So you have minus W2 cos beta 2 and minus W3 cos beta 3. Now, if I say W1A1 is the relative volume flow rate to section 1, Q, volume flow rate, so this moving control volume. Okay. I've written Q with a superscript flow because elsewhere I've used Q for the heat. Okay. Energy transfer as heat. So I'm putting a superscript flow here. So you'll recognize that this first quantity is minus of Q1 flow. Okay. And similarly, W2A2 if I call Q2 and W3A3 I call Q3 with a superscript flow, then you can write it as, instead of writing W2A2, for convenience I've introduced this notation. Okay. And here W1 is Vj minus U. Now in the one of the previous classes, I have shown you that when you apply Bernoulli's equation in the translating frame along a, of course here there's a slight error, it should be a relative streamline. Okay, I'll make the correction before I upload it. At the free surface, so we have shown that if the change in gravitational potential energy is small, the change in pressure is zero because this is a free surface, that is the interface between the liquid jet and the atmosphere. So pressure there is atmospheric pressure. So the change in kinetic energy in the moving frame is zero. So W2 is roughly equal to W1. So the relative speed magnitudes are the same, which is the assumption which is stated without justification in many books on fluid mechanics. So W2 you can say is approximately Vj minus U, and similarly W3 also will be Vj minus U. So if you go back over here, this W1, the speed, and this W2 speed here and this W2 speed, they all will be the same, and it will be equal to Vj minus U. So one can factor out rho times Vj minus U from all the three terms on the right hand side of this equation. Note that this is a scalar equation. And you have minus sign in all the three terms. So you can factor out the minus sign also and write it as minus times the density times the relative speed Vj minus u at the inlet as well as the two outlets. And then you are going to have Q1 flow plus Q2 flow cos beta 2 plus Q3 flow cos beta 3. See, the cos beta 2, cos beta 3, they remain as it is. Okay. Only thing we have recognized is the W2, W3 and W1 are the same and they have been factored out. Okay, now when the blades are symmetric, beta 3 and beta 2 will be the same. So I've simply called it beta without a subscript. So suppose I say beta 2 and beta 3 are beta. Then these two terms will be multiplied by cos of beta, which you can factor out and write it as Q2 plus Q3, the sum of this into cos of beta. Now let us apply global conservation of mass to the translating control volume. Then you will have W dot dA is 0. Now here the density of the liquid is constant. So conservation of mass is equivalent to conservation of volume. Okay, so I have not written the volume. And again, this can be split into 4 integrals. And on the last integral is 0 because this is a relative stream surface. Okay. And the first integral is minus W1A1 plus W2A2 plus W3A3. The sum of this will be equal to 0, which means that W1A1 will be W2A2 plus W3A3. Or I can say Q1 is Q2 plus Q3. So since the density is the constant, if you go back and look at the control volume, the volume flow rate of water entering Q2 is equal to the sum of the volume flow rate exiting through Q3 as well and Q2. Because the density is constant, so no mass can accumulate inside the control volume. So the liquid will be pushed out here. Okay. So the sum Q2 plus Q3 then is Q1. Q2 plus Q3 is Q1. So if I go back and look at this equation, you have Q1 here and the sum Q2 plus Q3, which you can replace by Q1 and write it as Q1 plus Q1 cos beta. And then you can factor out the Q1 also and write it as minus rho Q into Vj minus U into 1 plus cos beta. So rho times Q you will recognize as the mass flow rate of fluid entering the control volume. Now this is equal to minus Fb, the external force on the blade which is acting in the negative x direction. So Fb then, which you had anticipated will be positive, you can see will be positive because U will be less than Vj. It is the mass flow rate rho times Q1 entering the translating control volume into the relative speed at the inlet Vj minus U into 1 plus cos of beta, which is the same as beta 1, beta 2 and beta 3. Now for what value of beta would you get the maximum? And if you look at the power developed, that is simply Fb times U. So you'll have one more U here, U times Vj minus U into 1 plus cos beta. So you can see that when U is 0, the power developed Pb is 0. Now that is obvious because then the blade is not moving, so no work is done. But this equation also shows that when U is Vj, again the power is 0. Because here the jet is not striking the blades or just narrowly missing. So the power developed is for a given flow rate, okay, is beta is also constant. It will depend on the speed U or equivalently the angular speed of the disk. It depends. So it is like a quadratic function of U. U times Vj minus U. Now if you wish, I can factor out a Vj square, multiply and divide by Vj. So I can write this as U by Vj. And this Vj by Vj will be 1. So you'll have 1 minus U by Vj. So you have a non-dimensional parameter which you may call the speed ratio. Okay. Now you tell me Suppose Vj is fixed, okay, and u is fixed. For what angle will this expression give you the maximum power?
Beta equals 0.
Beta equal to 0. Right. But beta equal to 0 is not practical. Okay.
Yes,
Let me go
Sudhir.
back and look at, I've discussed this of course before, but now we have the mathematics to back it up. You see that if beta is 0, then theta will be 180. Okay. So that means the liquid jet which will strike it horizontally, from the particle will move from left to right here. If beta is 0, then it will go back horizontally from right to left. That will theoretically give you the maximum power. But then what will happen is, if you look at this height of the bucket is small. Okay. And of course here I've just shown you a schematic where it's not split into two. Okay. In general, so here I'm not showing you the splitted plate. Okay. So if it is deflected by 180 degree, it will interfere with the jet which is coming in. Okay. So in practical designs, okay, you want the angle to be as close to 180 as possible. Okay. But it's not possible. So typically the angles will be between 160 and 170. Okay. So if you see angles, when I ask you to solve problems which are say something like 165 degrees or 175 degrees. Okay, I don't have to explain that it is the angle of deflection. So the jet is coming in this way and is deflected through this angle. If I just define if I give you the blade angle, the angle will obviously be less than 90. Okay. Now I've given you a lot of details and I've explained everything in rigorously. You will not find this much detail in any book. Okay. Now you tell me, if I say that Vj is fixed, okay, here, or even if I go here, suppose I say for what if Q flow is fixed, at what value of U will you get maximum power?
Vj by 2, Vj by 2.
Right. But of course, if I look at the power developed by single blade, this Q flow will also have another V minus U. Okay. But we are actually not interested in the power developed by single blade. We are interested in the power developed by the turbine as a whole. Okay. And we'll talk about it in the next class. But today, let me just say that the water which is coming out of the nozzle, it may simultaneously strike more than one blade. Okay. So therefore, the power developed by the turbine will be more than the power developed by a single blade. Okay. So what will happen is that we'll have a similar expression. Okay. But this Q1, instead of being Q1, it will be the total flow rate coming out of the nozzle, which will be Vj times Aj. Okay. In which case it will be a quadratic. But here actually, if you look at the power developed by single blade, it will be a cubic. Okay. Now, in the next class, I'll also talk about an alternative method for finding the net force on the bucket. See, since the blade is translating at constant velocity, its acceleration is 0. So the sum of the forces is 0. So the external force and the total force exerted by the pressure acting on the blade will be equal to 0. Now, so you can integrate the pressure distribution and find out the force acting on the blade, and having found the force acting on the blade, you can find the power by multiplying it by U. Okay, but then you need to know how pressure varies with position along the blade, and for that you have to solve a differential equation, which will be a nonlinear equation. So that is not easy. However, I'll show you in the next class that the integral of P and dA here, that can be easily found by using a control volume approach. So in the next class, I'll use a different control volume, one which will not cut through the solid surface. I've already introduced this to you before when we talked about the forces. So one of the problems with drawbacks of this control volume is that you might ask that when Reynolds transport theorem was derived in the class, in your second year class, you did not look at the solid region, you looked only at the fluid region. So in the next class, I'll take a control volume with one surface coincident with the wetted surface of the bucket and show you that you can get the same result. So that doubt which you might have in your mind, that how can you apply Reynolds transport theorem when the control volume includes the solid, that doubt will be removed. Okay. And the second thing is that it will also give you a physical feeling about the origin of the forces acting on the plane. So if you look at just the pressure force acting on the blade, the pressure force on the wetted surface of the bucket will be more than the pressure force on the other side. Okay, so that physical feeling will also be conveyed to you. And the reason for that is when the streamlines are moving in this curved path, there will be a centrifugal force because of which the pressure will increase from atmospheric pressure at the free surface to a value which is larger than atmospheric pressure. So the gauge surface, the gauge pressure on the inside wetted surface of the vane will be positive. It will not be 0. The gauge pressure on this surface is 0. Okay. And the reason why the jet is deflected also I have explained to you. It is because the solid surface is impermeable. It does not allow the fluid to penetrate. So it has to turn. And this being an inviscid model, the fluid at the wetted surface will slip along the surface, and the direction of the velocity vector at each point in this model will be tangent to the surface. And we are assuming that at the exit also it remains tangent. But at the exit sometimes it may not exactly remain tangent because on the other side of the exit there is no solid. But we usually make the assumption that the velocity triangle is such that the relative velocity vector is tangent to the surface. Okay. Now this concept we'll be using again and again in other, while we analyze the turbine and the Francis turbine and the centrifugal pump. So I want to emphasize that the notation is the blade angle beta is the angle between the vector minus u and w, the relative velocity and this. Okay. Now, any queries? If not, then I'll stop here today.